So in this video I'd like to do a slightly more difficult example of a contour integral. So here I'm asked to show that the integral from 0 to infinity of the logarithm of x divided by x squared plus 1 dx is equal to 0. And of course by log here I mean the natural log, not log base 10 or anything like that. Okay, so the first thing I want to do is let's think about what kind of contour I want to use. Well, in all my previous examples I've always been using a semicircular contour. But that's not going to work here, because if I did have a semicircular contour, it would have to go through the origin. And the logarithm, as you know, is not defined at the point 0. So to get around that, I'm going to have to modify my contour slightly. So I'm going to do the following. So instead of drawing a semicircle, I'm going to start here, and I'm going to draw a line out here. Then I'm going to go around, so this is what I usually do with a semicircle, like so. Then I go inwards, and then I'm going to make a smaller semicircle inside. So what I've done is I've essentially done the same thing as my semicircular contour. I've just nudged it up a little bit so I don't have to pass through the point 0. So let's see what I've got here. Well, I want this larger circle to be of radius big R, so that's capital R, and I want this smaller circle to be of radius little r. So then the corresponding points on the other side will have to be minus capital R and minus little r. So this is centered at the origin, and it's going to be traversed counterclockwise. So I'm going to have arrows here, so I'm going to start here, go along here, go along this curve, like so, along here, and then finally back where I started. Okay, and I'm going to call these curves gamma sub r. So let's call this little curve gamma sub little r, and let's call this bigger curve gamma sub capital R. Now before I go on any further, I want to say that without loss of generality, I can assume that big R is greater than 1 and little r is less than 1. And both of these numbers are positive, by the way. The reason I'm doing this is because you might notice that I'm going to have a pole at some point at the point I. And I want that point to lie inside the contour. I definitely don't want my contour to be passing through that point. Not only that, but in the end, I'm going to want little r to go to 0, so I'm going to basically shrink this around the point 0, and I want big R to go to infinity. Okay, so now that I've chosen my contour, let's see if we can try to define a function for my integrand. Okay, so as usual, I'm going to let f of z be the log of z divided by z squared plus 1. But there's a problem here, because I haven't defined what this log means. It's a complex logarithm. So what does that mean when I say the complex logarithm? Well, actually there's another video on my channel where I've talked about the complex log, and I'll put a link to that in the description box below. So if you recall, the complex logarithm is defined in the following way. So I said that the log of z was the natural log of the modulus of z plus I times the argument of z. And remember, the argument of z is just the angle that the complex number makes with the positive real axis. So if I had a complex number here, the argument of that complex number would just be the angle it makes with the positive real axis. So in other words, if I had a point here, and I drew a line going up to that point, then the argument of that complex number would just be this angle here. So that's what the argument means. But what is the argument in this situation? Well, usually when I define the principal branch of a logarithm, I would always say that I would restrict the argument to the following inequality. So I'd always say that minus pi is less than or equal to the argument of z, which is less than pi. But there's another problem here, because if we look at the contour that I've actually chosen, you'll see that my contour passes right through the negative real axis, and that's exactly where my branch cut is, because if it's from minus pi to pi, then my branch cut is going to occur here. So in this region here, that's where my branch cut is going to be. And I can't do that, because remember that the complex log is going to have a discontinuity wherever I've defined the branch cut, and my contour is not allowed to pass through a point at which my function is not continuous. So to get around that, I've got to define another kind of branch, a non-principal branch, which means defining the log in a different way. So let's do that. So we're not going to define the log like this. So what I'm going to do instead is I'm going to restrict the argument of z to another inequality. So I'll say instead that I've got minus pi over 2 is less than or equal to the argument of z, which is less than 3 pi over 2. So now where is my branch cut? Well, it starts at minus pi over 2. So where is minus pi over 2? Minus pi over 2, that's the argument, is along here. Then I go all the way around and end up at 3 pi over 2. So my branch cut is actually going to be along the negative imaginary axis. But that's not a problem, because my contour does not actually touch the negative imaginary axis. So even if there is a discontinuity here, it doesn't really matter. Okay, so now that I've defined my function f of z and I've explained to you what the complex logarithm means in this situation, I can start trying to solve the integral. So let's set up my contour integral. Okay, well, by construction, let's see what I've got. So I've got let's do it in yellow. So I've got the integral over my contour C, that's what I'm calling this whole semicircular contour, of f of z dz. That is just equal to the, well, where do I start from? Well, I start from here, from little r, and I go up to capital R. So it's going to be the integral from little r to capital R of my function. And my function was log x over x squared plus 1. Well, is that going to be a problem? What's the definition of log along the positive real axis? Well, if I've got a positive complex number, well, a positive real number that is, that lies on the real axis, then the modulus of that number is always going to be positive. So I can immediately drop the modulus sign here. Not only that, but if I've got any number on the positive real axis, say like 15 or something, then the angle that makes with the positive real axis is just 0. Right? The angle this line makes with itself is 0. So the imaginary part of this complex logarithm is going to be 0. So I can actually just write this whole thing as the log of x divided by x squared plus 1 dx. Okay, so that takes care of that contribution. What happens next? Well, when I'm integrating over here, I've then got to integrate over this semicircular arc. So what's that going to be? That's going to be the so plus the integral over gamma sub capital R of f of z dz. Alright, so when I've done that, what happens next? Well, I'm going to be integrating from minus capital R to minus little r. So plus the integral from minus capital R to minus little r of my function. Now, you might think that, or you might be tempted to write log x over x squared plus 1, but actually there's a mistake there, because notice that I'm now integrating along the negative real axis in this direction. And now, the modulus of a negative number is a positive number, but the argument of any complex number that lies on a negative real axis is going to have an argument of pi, because if you have any sort of line along this axis, and I measure the angle it makes with the positive real axis, then that's just going to be an angle of 180 degrees, or pi radians. So what I actually have to write here is not just log, but I've got to write the log of the modulus of x, because x could be negative in this situation, plus I times the argument of x, which is just pi. And that's just, as usual, divided by x squared plus 1. I don't have to change this. Okay, and now I've got one more semicircular arc to deal with, and that's this semicircle here. So I've got to integrate over gamma sub little r. So plus the integral over gamma sub little r of f of z dz. Okay, so now what do? Well, the first thing I notice is that I've got z squared plus 1 in the denominator. Okay, well, I can easily I can factorize this in the following way. So z squared plus 1 is just z minus I times z plus I. So you'll see that I'm going to have a pole at z equals I, of order 1, and I'm going to have a pole at z equals minus I, also of order 1. So where are these on my arctan diagram? Well, I'm going to have a pole at minus I, so minus I, and I'm going to have a pole at I. And remember, this is why I chose r to be greater than 1 and little r to be less than 1, so that my pole definitely lies inside my contour. Now obviously the only pole that lies inside my contour is the pole at z equals I. So this is the only pole that I need to worry about. So I can quite happily use the residue theorem here. So let's calculate the residue of my function at this pole. So what happens when I do that? Well, I'm going to get, let's see, the residue of my function f of z evaluated at the point z equals I. By definition, that's just the limit as z approaches I of z minus my pole, so z minus I times f of z. What is that? Well, that's the limit as z approaches I of z minus I times the log of z divided by z squared plus 1. Well, remember that z squared plus 1 factorizes in this way, so I can simply cancel out a factor of z minus I. Well, let me show you how that works. Well, I can write this as z minus I times z plus I, and I can cancel out a factor of z minus I, like so. So then I'm just left with the limit as z approaches I of the log of z, all divided by z plus I. So now I can just quite happily plug in z equals I. So then I'm going to get the log of I divided by I plus I, which is 2I. Now I've got to use again my definition of the complex logarithm, because I is a complex number. Remember that the log of a complex number was log of the modulus of that complex number plus I times the argument of that complex number. So in other words, this is just the log of the modulus of I plus I times the argument of I divided by 2I. Well, the modulus of I is just 1, and the log of 1 is 0, so this term here is 0. So this term here is 0. But what about this term? Well, what's the argument of I? Well, remember, the argument is the angle that the complex number makes with the positive real axis. And I is somewhere here. Well, it's exactly here. And the angle that makes with the positive real axis is 90 degrees, or in other words, pi over 2 radians. Alright, so the argument of I is pi over 2. So if I put in pi over 2, I'm going to get I times pi over 2 divided by 2I. The i's are going to cancel, and I'm going to be left with, I guess, pi over 2 over 2, which is pi over 4. Okay. Now by the residue theorem, I can say that my contour integral, so the integral over my contour C, my function f of z dz, that's 2 pi I times the sum of my residues. So that's 2 pi I times the sum of my residues, so that's times pi over 4. And that's just 2 pi squared I over 4, so that's 2 pi squared I over 4, which simplifies as I pi squared over 2. So that's what I get when I use the residue theorem, and that takes care of the left-hand side. Because now I can say that this thing is just I pi squared over 2. Alright, so now that I've dealt with this contour integral, now let's look at this bunch of integrals here, where I've got 4 different integrals here. That's quite a lot. So let's deal with the integral over the larger semicircular arc first. So I'm dealing with the integral that varies along this curve here. So what happens when I do that? So let's look at the integral of gamma sub r. Well, I want to use the estimation lemma here. And remember, the estimation lemma says that if I've got my integral over gamma sub capital R of f of z dz, and I take moduluses like that, so the the absolute value of this integral, that's less than or equal to the length of gamma sub r multiplied by the maximum value of my function as it varies along this curve, the maximum value of the modulus of that function. So the maximum value of f of z, so that's the maximum value of log of z divided by the absolute value of z squared plus 1 as z varies along the curve. Okay, so that's what the estimation lemma tells us. Alright, well, notice what is the length of gamma sub r? Well, gamma sub r is just this larger circumference, and that has length pi r, because if you think about it, this is just part of a circle which has radius capital R. So if this were a full circle, it would have length 2 pi r, and since I'm only using half of that, its length is just pi times r. So this is just pi r. That's pi r. Now I've got to deal with this. So what do I do about the absolute value of log and modulus of z squared plus 1? Well, I can develop a series of inequalities that might help me here. So what do? Well, on gamma sub r, it's a semicircle of radius capital R. So every point on that curve has got to satisfy modulus of z equals r. Okay, well, how does that help me? Well, if I look at the denominator, I'm going to see if I can bound this denominator. So what can I do? Well, I've got modulus of z squared plus 1. Well, I can use the triangle inequality here, the reverse triangle inequality, which is going to tell me that this is greater than or equal to the modulus of z squared minus 1. But the modulus of z is just r. So this is just r squared minus 1. Now I've got to deal with this logarithm stuff. Well, what happens if I take the absolute value of this logarithm? Well, the modulus of the logarithm, that's just equal to the modulus that's just equal to the modulus of the log of the absolute value of z plus I times the argument of z. Alright, well, again using the triangle inequality, that's less than or equal to the modulus of the log of the modulus of z, modulus, plus some stuff. Well, plus the modulus of I argument of z. Well, the modulus of I is always 1, as you've just seen, so I'm just left with, let me create some space here, so modulus plus the absolute value of the argument of z. Okay, well, the log of the modulus of any number is always going to be positive, so I can drop these modulus signs like this, so I don't need these. Well, what about the argument of z? Well, if we look at gamma sub r, so the argument of z is the angle that this curve makes with the positive real axis. So as it varies along this curve, the largest argument that I'm going to have is going to be the angle that it makes here. So if you notice, if I go along here, I've got an angle of 90 degrees, 100 degrees, 110, until I get to 180, or pi radians. So the absolute, the largest angle I'm going to have is going to be 180 degrees, or pi radians. So I can bound the argument by exactly pi. So this is less than or equal to the log of the modulus of z plus pi. But the log of the modulus for z, well, modulus of z is r, so this is just simply log of r plus pi. So now I've bounded both of these quantities. So how does that help me? Well, that tells me that the absolute value of my integral, sorry, that's not the contour integral, that's the integral over gamma sub r of f of z dz, that is going to be less than or equal to the length, which I've established was pi r, times the maximum value of my function. Well, I can say that that's less than or equal to log r plus pi, so I'm going to have log r plus pi, and in the denominator, well, you notice that I had modulus of z squared plus 1 is greater than or equal to r squared minus 1. I take 1 over that, so I take the reciprocal of both sides. This sign becomes a less than or equal to sign, and what I end up with is this thing divided by r squared minus 1. So what happens to this expression as r goes to infinity? So as r goes to infinity, what happens? As r goes to infinity. Well, this thing is going to go to 0, and I'll show you why. Well, when I expand this, I'm going to get pi r log r plus pi squared r divided by r squared minus 1. Now obviously pi squared r divided by r squared minus 1, that's going to go to 0 because the degree of the polynomial in r in the denominator is obviously greater than the numerator. But what about pi r log r divided by r squared plus 1? Why does that go to 0? Well, the sort of intuitive way you can think about this is that log r grows much more slowly than r does as r goes to infinity. But if you don't like that sort of hand-wavy explanation, then all this really requires is evaluating the limit of so limit as r goes to infinity of log r divided by r. So what happens to this? Well, I've got infinity over infinity, so I can use L'Hopital's rule, and that tells me that that's the limit as r goes to infinity of 1 over r divided by 1, and that's obviously 0. So that's why this expression goes to 0. So what does that tell me? Well, that tells me that the contribution of this integral, so that's this one, this thing is as r goes to infinity is just going to contribute nothing. So that deals with that integral. What about this integral? Well, it's going to follow exactly the same sort of pattern. So if I try to use the estimation lemma again, what happens? So the estimation lemma tells me that the modulus of the integral over gamma sub little r of my function f of z dz, what's that? Well, that's less than or equal to the length of gamma sub little r times the maximum value of my function, which is the modulus of the log of z, all divided by modulus of z squared plus 1, as z varies along that part of the curve. Well, again, this length is just going to be pi times little r, as we established before. That's just with the smaller semicircle. Now I've got to deal with this thing. Well, I can use exactly the same technique. I can say that the modulus of the log of z, that's just the modulus of the log of the modulus for z plus the argument of z, and that again is bounded by log of little r plus pi in exactly the same way as I've just done. So what about modulus of z squared plus 1? Well, I'm going to do this in a slightly different way. I'm going to say that the modulus of z squared plus 1, I'm going to write that instead as the modulus of 1 plus z squared. And again, if I use the reverse triangle inequality, that is greater than or equal to 1 minus the modulus of z all squared, which is just 1 minus little r squared, because every point in this curve has got to satisfy a modulus of z equals little r. It traces out part of a circle of radius little r. Alright, so what happens now? Well, if I plug these two bounded quantities into my inequality, what do I get? Well, I'm going to get that the modulus of the integral of my function over gamma sub r, so f of z dz, that is less than or equal to pi times little r times some stuff. Well, on the top I'm going to have log of r plus pi, and on the denominator I'm going to have 1 minus r squared. So what happens to this thing as r goes to 0? So as r goes to 0, this whole thing also goes to 0, and I'll show you why. Well, if r goes to 0, then obviously in the denominator I'm just going to get 1 minus 0, which is 1. So if I expand the top out, I have pi r log r plus pi squared r divided by 1. Well, pi squared r obviously goes to 0 as r goes to 0, so I don't need to worry about that. The main issue is looking at why pi r log r over 1 minus r squared goes to 0. So what I actually want to justify is why is it that the limit as r goes to 0 of r times log r Well, why is that limit 0? Well, this is actually a standard problem in analysis that you might see in sort of a first year analysis course, but I'll quickly show you why this is true. Well, if I plug in 0 here, I'm going to have 0 times the log of 0, which I guess is minus infinity. And because that's an indeterminate form, I can use L'Hopital's rule here. So what I'm going to do is I'm going to write this as the limit as r goes to 0 of the log of r, and instead of multiplying by r, I'm going to divide by 1 over r. Notice that this is exactly the same thing, because if I multiply the top and the bottom by little r, I'm going to get 1 here and r in the top to give me the same expression here. So let's use L'Hopital's rule. What happens to this? Well, if I differentiate the top, I'm just going to get the derivative of log r, which is 1 over r. And on the bottom, I'm going to get the derivative of 1 over r, which is minus 1 over r squared. Okay, well, let's multiply the top and the bottom by r squared. That's the limit as r goes to 0 of, well, r squared divided by r is just r, divided by minus 1. And the limit of this thing as r goes to 0 is obviously 0. So that's how we do that. So now we've shown that this whole quantity, the absolute value of this integral by the estimation lemma, is going to go to 0. So what I've shown you is that the contribution, if I scroll all the way back up, so the contribution of this integral here is also going to be 0 when I take the limit. So now what happens when I take the limit of my contour integral as r, little r goes to 0 and r goes to infinity? What happens? Well, on the left hand side, as I've just shown you, I'm going to get I pi squared over 2. Did I write that down somewhere? Yeah, I pi squared over 2. So that's here. So on the left, I'm going to have I pi squared over 2, which I showed you using the residue theorem. What's that equal to? Well, look at what integrals I had here. Well, these things in the limit, these two integrals here both go to 0, so I'm not going to have to worry about writing these down, because their contribution is 0. Well, if little r goes to 0 and big R goes to infinity, this integral is just going to integrate over the whole positive real axis, because I'm going to start at 0 and go out to infinity. In exactly the same fashion, here I'm going to go from minus infinity all the way to 0. So if I write all that out, what happens? Well, I'm going to have the integral from 0 to infinity of the log of x, all divided by x squared plus 1 dx. Okay, and now for my other integral, which is going to go from minus infinity to 0, it's not just going to be log x. Remember that it's going to be the log of the modulus of x plus I times pi, all divided by x squared plus 1 dx. Well, this is the integral I'm after, so I want to see if I can deal with this contribution first. Well, let's expand this. That's going to be the integral from 0 to infinity of the log of x divided by x squared plus 1 dx, plus the integral from minus infinity to 0 of log of the modulus of x over x squared plus 1 dx. Well, I pi is a constant, so I can just pull that out of the integral, so that's plus I pi times the integral from minus infinity to 0 of 1 over x squared plus 1 dx. Okay, well, this is the integral that I'm after. What's this thing? Well, I'm integrating the log of the modulus of x over x squared plus 1 from minus infinity to 0. Well, notice that this thing is actually an even function. So if I put in minus x instead, if I made the substitution, I would end up with exactly the same function. So what I can actually say is that these two integrals are exactly the same, because the integral of this thing from minus infinity to 0 is going to be the same as the integral from 0 to infinity, because it's an even function. Okay, so this is just going to be twice the integral from 0 to infinity of log of x all over x squared plus 1 dx, because these are the same integral, plus I pi times this integral, plus I pi times this integral. Well, you might remember that this integral is just arctan x, which I did a previous video on, I think in contour integration part 1 or something like that. Well, I've shown you why this integral is arctan x, or you can just use a trig substitution if you like. So this is going to be arctan x, or inverse tangent of x, from minus infinity to 0. And what's that going to be? Well, I'm going to end up with twice the integral from 0 to infinity of the log of x divided by x squared plus 1 dx plus I times pi times some stuff. Well, the arctan of 0 is 0 minus the arctan of minus infinity. Well, I really should be taking limits here, but if I take the limit of arctan of x as x goes to infinity, that's going to be pi over 4. The arctan of, well, arctan is an odd function, so arctan of minus x is minus arctan of x, so this is going to be a plus sign, and arctan of infinity is pi over 4. Alright, so that's just going to be twice the integral from 0 to infinity of the log of x divided by x squared plus 1 dx. Well, 0 plus pi over 4 is pi over 4. That's going to be I pi squared over 4. Okay, and now I just take real parts of both sides, and what I should get is that twice the integral from 0 to infinity of log x divided by x squared plus 1 dx, and that's telling me that that's equal to 0 when I take real parts of both sides, so I don't need to talk about the imaginary parts. But if I then divide both sides by 2, that tells me that the integral from 0 to infinity of the log of x divided by x squared plus 1 dx, that is equal to 0. So that's how we solve a contour integral involving log. If you like what you saw, make sure you like this video, comment and subscribe, and make sure to check out our Facebook and Twitter pages in the description box below. See you next time.